Oh, hey guys. So we are going to work on today something that's called optimization. Really, that's just taking our knowledge now of derivatives and finding maxes and mins and applying that to word problems. This is very, very applicable to engineering or physics or like any kind of hard science where you can set up a model mathematically and you want to find the optimum values for that model. Now, all of these questions are a little different, but they all have some key similarities. And since I'm gone today, I'm going to be asking you guys to work on some of those problems. I have here an example problem. I will do this example with you, and hopefully that will give you a little bit of an idea how to tackle some of these problems. And of course, we'll take up lots of these problems when I'm back. Okay, so this problem is saying, okay, we have a box, and this box has a square base. So the base, square base, it has x and x as its side lengths. Let's call them x. And it has some other height. The height of this box is not necessarily the same as x. Maybe it's really narrow and tall, or maybe it's wide and short. We don't know. What we do know is that the volume of the box is 32,000 cubic centimeters. Now, okay, what is the volume of this box? The volume of this box, okay, is every sentence you should generally try to translate into something mathematically. So if I tell you the volume of the box is 32,000 centimeters cubed, you're probably going to need that somewhere. So let's figure out volume is base times width times height. So it's x times h, which we can simplify as x squared h, and since we know the volume, 32,000 equals x squared h. Okay. Now, what are we actually trying to solve? The next sentence reads, find the dimensions of the box that minimize the amount of material used. So we want to basically manufacture this box as cheaply as possible. In doing so, we need as little material as possible. So the surface area, which tells us the amount of material used to build this box, is you add up all of the sides of the box, the area of each side. So the bottom of the box, let's think of our box, maybe the bottom of our box, this is the bottom, the front facing face here, has area x times x squared. The height, remember these are the heights. There are four sides that are exactly the same as this red side here. Okay, there are four sides like that. Those each have area. So there's four. They each have area x times h. Yes, this is x. And what about the kind of the side we can't see directly opposite the closest face? That we have an open top box, open top. So there is no side there. So the surface area, the total surface area of this box is indeed x squared plus 4xh. Now, what we want the minimum surface area. Remember, from the first term, we know that a function has a minimum when its derivative is 0. So what we would like to do is we would like to calculate the derivative of the surface area. Instead of dy dx, we have dsa dx because our y here is really our surface area. Now, the problem is we've got two variables on the right. We've got an x, and we've got an h. And really, we only have to do derivatives when we have one independent variable. However, we're not out of luck here. We can replace our h with an x by looking at this equation. This is totally equivalent, since x can't be 0, to saying h is 32,000 divided by x squared. And we can now substitute this. This is something that comes up in almost all of these problems. We have two relationships. One where it's known, the volume is known, which we use to substitute. This is a constraint on our problem. And the other is something we want to maximize or minimize, which we need to substitute into and take the derivative. So we have, actually, you know what, let's just look at surface area is x squared plus 4x times, instead of h, we have 32,000 over x squared, which is x squared plus 32,000 times 4 is 128,000. I'm going to call this x to the negative 1. You could do over x. And let's take its derivative. A lot of you guys would want to write that as the derivative, prime. The other notation is a little clearer. It tells us which variable we're differentiating with respect to. And this is 2x minus 128,000 x to the negative 2, which is really 2x minus 128,000 over x squared. And we're going to set this equal to 0. Remember, maxes and mins occur when the derivative is equal to 0. So if we want to find the minimum possible surface area, we take the derivative, set it equal to 0. I'm going to multiply everything here by x squared. So 0 equals 2x cubed minus 128,000. And so x cubed is 128,000 divided by 2. So x is equal to, what is 128,000 divided by x cubed is 64,000. Therefore, x is 80. It should be 40. I was thinking of x squared. 40. Now, how do we know this is actually a max or a min? Well, I'm going to check using the second derivative test, where I can just plug in a stationary point, a point where the derivative is 0, into the second derivative, and hopefully the sign of the second derivative tells me it's a max or a min. So the second derivative, now this notation is weird. We did look at it in class, but it's pretty strange. 2 minus or plus 128,000 times 2 over, if you do it out, you'll get this. And since x is always positive, this expression here is always greater than 0. Therefore, we have a minimum surface area when x equals 40 centimeters. And we can also get the height of the box. Remember, the height is 32,000 divided by x squared. So the height, I'm going to get rid of this annoying gray screen. Paper size. The height is 32,000 over x squared, which is 40 squared, which is 32,000 over 1,600, which is equal to 20 centimeters. So this box, which has to have a volume of 32,000 centimeters cubed, will have a minimum surface area when x equals 40 and the height is 20. So review this carefully and try some of the problems I've left for you on these homework pages. Basically, they always have two equations. One is called a constraint, where they tell you the exact volume or the exact surface area or some other quantity, and you use that to substitute into the equation that you actually want to maximize or minimize, which you take the derivative of, set it equal to 0. Thanks.